Hello all, welcome back to the channel. In this session, let us see the next example based on balancing of rotating masses. The question is like this. 4 masses M1 equals 100 kg, M2 equals 175 kg, M3 equals 200 kg and M4 equals 125 kg are fixed to a crank of 200 mm radius and revolve in planes 1, 2, 3 and 4 respectively. The angular positions of the planes 2, 3 and 4 with respect to 1 are 75 degree, 135 degree and 240 degree taken in same sense. Distance of planes 2, 3 and 4 from 1 are 600 mm, 1800 mm and 2400 mm. Determine the magnitude and position of the balancing masses at radius 600 mm in the plane L and M, located in the middle of 1 and 2 and in the middle of 3 and 4 respectively. The moment the question is read, it seems to be there is more data given to us. Let us break down the question one by one. The first thing is, let us take down the question towards the side of the paper. Clearly mentioned 4 masses M1, M2, M3, M4 each is having its own magnitude and all the masses have the same radius, that is 200 mm. Apart from the 4 existing masses, there are 2 balancing masses. Those balancing masses are represented as L and M. These two are having a radius of 600 mm. It's a very simple analysis. There are 4 masses, 4 different masses. In order to balance these 4 masses, 2 extra masses are attached. The angular positions are 75, 135 and 240 degrees from mass 1. Let us see the step-by-step procedure how to obtain the solution. Before starting the solution, let us see what is that we should find out. The magnitude and position of the balancing masses has to be found out. That's it. There are 2 balancing mass, L and M. Its magnitude and position has to be found out. The value of balancing mass and the angular position has to be found out. So this is our target for this question. The first step here is obtain the planar diagram. The question is, what is planar diagram? Since clearly mentioned all the 4 masses are revolving in 4 different planes 1, 2, 3, 4, we are just representing this on the sheet of paper. Yes, this is a common crank. All the masses are now connected to the common crank. I will call this as plane 1. This is the plane 2, 3 and the 4. Clearly mentioned the distance of planes 2, 3 and 4 from 1 are 600, 1800 and 2400. If this is the plane 1, the distance between these two clearly mentioned it is 600 mm. Let us update these values. This value is 600 mm. Similarly, the distance between the plane 1 and 3. 1 and 3 are 1800 mm. The distance between 1 and 4 is 2400 mm. I will take a moment and I will update the values. Yes, let me show a small representation of a mass here. So this is, we can call as M1, that is equal to 100 kg. Similarly, this is 175 kg, 200 kg and 125 kg. And the next data clearly says all the masses are fixed to a crank of 200 mm radius. all the four masses is having a common radius that is nothing but 200 mm. Show the value of radius 200 mm. 200 mm is nothing but 0.2 meters. What is that we have left out from the question? There are two balancing masses, L and M. This is having a radius of 600 mm, that is nothing but 0.6 meters. Initially this was 200 mm, this is 0.2 meters. Now the balancing masses are rotating at a radius of 600 mm, that is 0.6 meters. The balancing masses are kept in the planes L and M. But the question is, where is L and M? Clearly mentioned, L is located in the middle of 1 and 2. One plane is here, the second plane is here. In the middle of 1 and 2, I will show with the help of a black pen, I will show the balancing mass plane L. And M is placed in the middle of 3 and 4. Now, this would be the balancing mass plane M. I will call this one as M plane followed by L plane. And this is having a radius of 600 mm, 0.6 meters. Now, a simple analysis. The distance between 1 and 2 is 600 mm. Clearly mentioned the balancing mass L is in the middle of 1 and 2. That means to say that this distance is now divided. So this would be 300 followed by the remaining would be 300 mm. The complete distance here is 2400 mm. Now, don't you think the distance between the planes 3 and 4 is nothing but 2400 mm minus 1800, right? So this distance is now 600 mm. When a balancing mass is drawn in the middle of 600 mm, that means to say that the distance would be once again 300 and 300. You may be thinking that the distance are not in order. That means to say that it is not drawn as per the scale. Yes, the planar diagram need not be as per the scale. So if required, I will mention here, this is not to scale. This is just a normal representation. So with this minimum knowledge, let us go for step number 2, that is the space diagram. Do remember, in the space diagram, we should show only the angular positions. We have considered almost all the data in the planar diagram, but these 75, 135 and 240 degrees are not considered. Clear? Yes. Now let us consider these values. All these values, 75 degree, 135 degree and the 240 degree, are taken with respect to the first mass. So let us show the first mass along the horizontal. I will call this as a connected to a common crank. This is the point O. This would be the mass representation. Once again, this is MA with a value of 100 kg. This is with a radius R, that is equal to 0.2 meters. Now, I will make use of compass. I will mark 75, 135, 240 degree from the same point. Place a protractor at a point O. Mark 3 angles, 75, 135 and 240. For 240 degrees, let us keep the protractor in the opposite direction. Already we are having 180 degrees. Add 60 degrees to it. Let us make use of scale to show the radius and mass representation. And the space diagram has to be drawn as per the angular position, exact values. But we have mentioned the radius is equal to 0.2 meters here. The radius need not be as per the scale. All are in the same radius. I will maintain the same radius. I'm sorry, we cannot call this as MA. Why? Because in the question clearly mentioned this as M1. Make use of compass to show the angular position values. So now this completes the step number 2, that is the angular position diagram, that is space diagram. With this, let us go for tabular column. Step number 3, I will adjust here. What are the contents of the tabular column? The first thing is we have considered the planes and the masses in the each plane, radius of each planes in meters, followed by the centrifugal force, the product of column 2 and column 3. And let us consider one common plane as the reference plane and the distance from the reference plane, followed by, once we have got the distance here, we can multiply force into distance to get the couple, one by one. As seen in the planar diagram, the plane first is the first plane, followed by L plane, plane number 2, plane number 3, plane number M, followed by the fourth plane. I think it is cleared. What are the masses in each plane? So in this plane, we can call this one as M1, that is with a value of 100 kg already mentioned here. So this we are supposed to find out. Let us call this as balancing mass L. This is M2 with a value of 175 kg. This is M3 with a value 200, and this is once again balancing mass M. This has to be found out. I will keep within the question mark, followed by M4 once again with a value 125 kg. All are fixed to a common crank with a radius 200 mm. This would be R1 0.2 meters, R2 0.2 meters. But what in the case of balancing mass? RL with a value 0.6, RM with a value 0.6 meters. Let us check out the values of centrifugal force. Make use of calculator. 100 into 0.2 gives you the value of 20. This is unknown. I will keep as it is, 0.6 times the balancing mass L. The next is 175 into 0.2 gives you the value as 35. Similarly, 200 into 0.2, 40. Once again, this is unknown term. This is 0.6 times the balancing mass M. The last one here is with the value 25. The next column, distance from the reference plane. But the question is, which is the reference plane? Choosing a reference plane, it is completely your choice. It's left to you. You can choose any plane as the reference plane. As far as possible, do not choose the first and the last plane as the reference plane. Only if the situation demands, select first and second as the reference plane. Apart from that, you can choose any plane as the reference plane. And the second thing, we are having two unknown terms here. Don't you think if you select this itself as the reference plane, one column will be 0? So that we are minimizing the number of unknown terms. Hope you understood. If not, follow the procedure. Distance from the reference plane. Now I will call L as the reference plane. Distance from the reference plane, L. Now, don't you think the first plane is at a distance of 300 mm from the reference plane? Absolutely. This should be in terms of meters once again. So that would be 0.3 meters. Yes, your thinking is right. Since it is towards the left hand side, this value is negative. And distance from the reference plane L, this itself is the reference plane. Henceforth, this value is 0. Hope it is clear. Now, one unknown term is minimized already. The next, for M2, what is the distance between reference plane and second plane? 300 meters. Sorry, 300 mm, that is nothing but 0.3. This value is positive. Why? Because this is towards the right hand side. Distance of reference plane to the plane 3. Don't you think this is 300 plus this distance? Exactly. I will show here. You require a lot of patience to solve these type of problems. The question is, what is this left out distance now? Don't you think this left out distance here is 1800 minus 600 mm? So this from here to here distance is 1800 and this distance is 600. So this distance is 1800 minus 600 gives you the values of 1200. So the left out distance here is 1200 plus 300, that is nothing but 1500 mm. So I can update this value as 1500 mm. 1.5 meters, once again with a positive. Why? Because towards the right hand side. Similarly, what is the distance between balancing mass M plane to the L plane? From here to here. Don't you think this is 1500 plus the 300? Absolutely. That is 1800. That is 1.8. Similarly, the distance from reference plane to the last plane. How do you measure this one? From here to here is 1500 plus 300 plus 300. That is nothing but 2100 mm. That is 2.1 meters. Once again, make use of 200 into 0.3. Negative carry as it is. So this value is 0 followed by 35 into 0.3. Sorry, I think I made a mistake here. This is not 200 into 0.3. This is 20 into 0.3. That is the value 6. I will update now. This will be 0. Yes, it is correct. This is 35 into 0.3, 10.5 correct. 40 into 1.5, 60 it's correct. Followed by this is unknown term. I will keep as it is, but we can multiply 1.8 into 0.6. This is 1.08 times the balancing mass M followed by the last one. This is 52.5. Let us draw a couple polygon to obtain this unknown term. This unknown term can be substituted here to find out this value. Thereby we are done with the solution. The step number 4 here is the couple polygon. Concentrate only on the couple values. For this one, we require some scale factor. Now I will be considering the scale factor is equal to 1:5. That means to say that I am dividing the values by 5 times, 1 by 1. Now, it's better if you make use of a roller scale. The first value, 6. After considering the scale factor, the value becomes 6 divided by 5. That is equal to 1.2. This is along the mass 1. Let us see how to draw the couple polygon. The value is 6. Consider this 6 in the calculator divided by the scale factor. That is 5. Therefore, we are getting the value as 1.2. This is along the mass 1. And mass 1 here we have considered as 0 degree line. That is the horizontal. Make use of roller scale on any convenient plane. Draw 1.2 centimeters. I will call the first point as O and the second point as A. We are moving towards the left hand direction for the reason the 6 is negative 6. Moving further, the balancing mass value here is 0. The couple on M2. The couple on mass 2 is 10.5. Once again, make use of calculator to get the reduced value. 10.5 divided by 5 is nothing but 2.1. Once again, make use of roller scale. Keep your roller scale along M2 from the space diagram. That is at an angle of 75 degrees. Move the roller scale towards the point A. Draw one more parallel line. What is the dimension? Already we have mentioned it is 2.1 centimeters. Now make use of your compass. Measure 2.1 centimeter, cut an arc. The extra lines not required, you can remove it. So at this point, draw one more reference line. The next value is 60. 60 divided by 5 would be equal to 12 centimeters. Yes, it will cross this area. Kindly accept it. But what is the angle? Angle, it is on mass 3, that is 135 degree. Make use of roller scale. Keep your roller scale on M3 plane. Move the roller scale towards the new point. From the new point, draw one line. Now make use of compass. Measure 12 centimeters. This point as the reference, I will cut an arc. Once again, you can draw one more reference line here. The next plane, M4 plane is 240 degree. So move the roller scale. At this point, just draw the line. But what is the dimension? It is 52.5. Once again, 52.5 divided by 5 would be the value 10.5. Measure 10.5 centimeters in the normal scale. From this point, mark 10.5. Once again, we can draw one more reference line here. I will call this point as point B followed by point C, and this is the point D. Now make use of scale. One should be careful. Let us connect point D to the point O, not to the point A. The first point was A, right? This is the unknown term. We wanted to close the polygon here. Keep the scale. Draw a dotted line. This is the unknown term. I'll make use of compass to show the angular position. So this completes the couple polygon. So what is that mistake we have done? Yeah, actually it's not a mistake. So what is that we could have been avoided? This couple polygon would have been drawn in such a way that it is not merging with the data. What is that best we could have done? Instead of taking the scale is equal to 1:5, we could have increased the scale factor. We could have taken 1:10 so that these values get reduced by 10 times. Absolutely no issues. You can go with scale factor 1:10 and you can plot the same sketch. The sketch would be the same. Even answers you will be getting the same thing. Now we have completed couple polygon. We can go for force polygon. So before going for force polygon, let us find out the unknown terms from the couple polygon. Therefore, this is a point D. D is connected to O. This is the angle 75, 135, 240 degree. This angle we were supposed to find out. Do you remember? The balancing mass L and M, magnitude and position has to be found out. So this is with respect to M. Let me call this one as theta of balancing mass M. So from the couple polygon, don't you think OD into scale? That is nothing but 1.08 times the balancing mass M. Now make use of scale. Check out the distance from O to D. O to D distance is nothing but close to 14.5. Be careful. Most of the students do check the value from D to A. This is not the distance. D to O distance is here. It's showing 14.5 centimeters in my normal scale into the scale factor. Initially we had taken scale factor is equal to 1:5. The scale is 1:5. We divided the scale values here. Henceforth, let us multiply the scale factor value, that is equal to 1.08 times the balancing mass M. Therefore, balancing mass M is equal to 67.12 kg. This is the first part of the answer. Followed by, what is this angle? Now, don't you think from here to here the angle is 180 degrees? From here to here, the angle is 270 degree. So let us check out this angle. There is a slight difference of 4 degree or 5 degree variation. I will make use of protractor. The angle is close to 354 degrees. So from this angle 180 plus 90 plus the remaining angle. So therefore, theta M is equal to 354 degrees. Measured in counterclockwise sense. So this completes the part of the solution. With this, I will proceed for step number 5. That is force polygon. I will be taking the same scale factor 1:5. The thing is, the space available is less here. You can see a few projections of what I have drawn previously. I had taken the scale factor 1:10. So what happens if you take 1:10? Yes, absolutely the sketch accommodates in this space, but that would be very small. But this is a tutorial video, right? So I thought of changing the mind and I changed the scale factor as 1:5 itself, so that the sketch is bit enlarged so that it is visible for you people clearly. Yes, let us go with the force polygon. Scale 1:5. The value after scale factor conversion would be 20 divided by 5. That is equal to 4 centimeters. I will make use of roller scale. This value is along M1. Keep the roller scale along M1 from the couple polygon, or you can take from the space polygon. It's left a space diagram. So that is nothing but the horizontal. Move the scale. Draw a line of 4 centimeters. This is the point O, this is the point A with the value 20. The second value here is unknown term. Please do remember, unknown term always keep it at the last. This is 35. 35 after dividing by scale factor would be 7, and this is on M2 mass. M2 mass is along 75 degrees. Keep the roller scale, move the roller scale towards the point A. Draw 7 centimeters line. Make use of your compass as usual, transfer 7 centimeters. So this would be the point B. The next value is 40. 40 after scale factor would be 8. That is along M3, and M3 is along 135 degree. From this line as a reference, move the roller scale towards the point B. Draw a line. What is the distance? 8 centimeters. This would be the point C. The next value, actually it was unknown term, but it is calculated now. Unknown term or the calculated value, keep it at last. The next value is 25 mm along the mass M4. M4 is along 240 degrees. Once again, we do have the line, constructed line here. Move the roller scale. Keep it at the point C. It's just passing the previous line, previous couple polygon. This would be the representation. But what is the distance? The distance is 25 divided by 5 with a scale value, that is 5 centimeters in the normal scale. So we have finished 25. We have got the point D here. Once again, go back to the first point 20. We have already considered 0.6 times the BML. Unknown term, keep it at the last. 35 considered, 40 considered. Now check out this value. This is nothing but 0.6 times the balancing mass M. This is 0.6 into balancing mass M. The value 67.12. That is nothing but, in the calculator, the value would be 40.272. This value is along the theta M, that is 354 degree. Once again, make use of roller scale. Keep the roller scale along 354 degrees. Move the roller scale towards the point D. Draw a line. The value is 40.272. It's still there in my calculator. Divide the value by its scale factor, that is 5. The value is 8.0544. Consider 8 centimeters. Point D as the center. Cut an arc at the point 8. It has just crossed the BC line. The point is here. That would be the point E. 25 once again over. 20 we have considered. 0.6 times the BML. To get the last point, join E to O. The unknown term has to be in the dash lines. So this is, we are moving in this direction with a value 35 followed by, this value is 40. This is with a value 25, and this is nothing but 0.6 times the balancing mass M, that is equal to 67.12 followed by, this is 0.6 times the balancing mass L. I will update the angular positions. Carefully observe here. I will make use of pen here. So this is the reference line. Exactly at the point D, draw one reference line. The reference line to the dotted line, we should check the angle, and that would be the angle theta L. Now what is that we have found out from the force polygon? So from the force polygon, unknown term has to be found out. That is nothing but EO into scale. 0.6 times the balancing mass L. What is the distance of EO? It's 9.3 centimeters in the normal scale, followed by the scale factor, that is 1:5. We had divided the scale values here. Let us multiply the scale values. 0.6 times the balancing mass L as it is. Therefore, balancing mass L is equal to 9.3 into 5 divided by 0.6. 77.5 kg. This is the next part of the answer. What is the angle? Therefore, the position, that is theta L, is equal to, make use of protractor. From here to here the angle is 180 degrees. Place a protractor on point E. This is 53 degree. 180 plus 53 degree. So that is 180 plus 53. That is nothing but 233 degrees. So measured in counterclockwise sense, this is the next part of the answer. So this is almost towards the end. As per the data, we were supposed to find out the magnitude and the position of balancing mass L and M. Magnitude is found out 67.12 kg followed by 77.5 kg. Position is also found out 354 degrees and 233 degrees. All are measuring in the counterclockwise sense. What is the last step? As I told you, at some point of time during the solution, the patience is the key. Generally, this question will be asked for 15 marks or sometimes 16 marks, else 20 marks. But it's worth for 20 marks. Have patience. Do it with utmost care. The last step here is come to the step number 2, that is space diagram. Show the position of the balancing mass. The first balancing mass is at an angle of 354 degrees. Keep the roller scale here. Now I will make use of pen for better clarity, for better visibility. So move the roller scale towards the point O. In a dash lines, show the value. What is the second value? The second value is 233 degree. Keep the roller scale here. Move the roller scale. What we have found out the magnitude and the position is shown on the space diagram. The only left out part here is the last part. Make use of a compass to show the position values. So this is with a value of 233 degree. This is with a value of 354 degrees. This completes the solution. Hope you have enjoyed this video. If yes, give this video a thumbs up and request you to share with your friends. Do not forget to subscribe. I will talk to you in the comments. Have a nice time. Thank you. Bye-bye.